Hello, I hope you have had a good session so far. This is our third presentation. I'm going to be talking about GIS and how we use it to characterize a watershed and parameterize the model. Some of the decisions we've made in terms of developing this application. Okay, and I'll talk a little bit about modeling in general. Okay, in terms of what kind of models are we using, as well as, level of accuracy that you can actually expect under different situations. All right. So basically, a hydrologic model is a tool that allows us to basically understand how water moves essentially through the environment, okay? And also helps us manage watersheds. Models synthesize data across the watershed. Each land use type can have a different response. What a model does is integrate that response, okay, those different responses to predict the response for the watershed as a whole. So we're really typically dealing with a complex landscape, multiple soil types, multiple land use types, different differences in terrain, different management actions being applied on the watershed. And that tool, that watershed tool, okay, watershed model allows us to synthesize all that information. Okay. Now, there are different types of hydrologic models. There's deterministic models and there's stochastic models. In AGWA, our models are all deterministic models. And what that means is that if for a given set of input, we will always get the same output. There's no stochastic or statistical parameters to look at the variability of the potential output you can have. Okay, so for a given input, you get the same output, just like a regression equation. All right. Now, models can also be based on fundamental laws. We call those physically based models, or they can be empirical models. They're just based on the data, like a regression equation, or there's some hybrid in between, some physical components as well as empirical components. Okay, in AGWA, we have several different models, okay, like Kinross and SWOT, where Kinross is a more physically based model, and SWOT is considered a bit more of a hybrid model. Some of its algorithms are more empirical. Okay, like SWOT will use the curve number technique to estimate runoff, and it will use the universal soil loss equation, which is definitely an empirical model to estimate erosion, but it's set in a physical framework, where when we're dealing with Kinross, we estimate infiltration using gradient amp, and we route water off of the hill slope using a kinematic wave approximation. So it's a more physically based model. Both the models are what we call distributed models compared to lump models. A lump model, a watershed is treated as one unit, okay? All the parameters are uniform across the watershed. Where a distributed model, and we'll talk more about this through this presentation, we've taken the landscape and broken it up into different, essentially modeling units. Each one of those modeling units can have a different set of parameters. In our case, with Kinross, as well as SWOT, we can also have different channel elements, and each one of those channel elements can have different input parameters. Okay, so we're looking at differences like in land use, soils, terrain across the landscape through these different modeling units. And that's what we're talking about here when I say submodel or sub-element. Okay, we're not using a grid model where we have grid cells that have input parameters, or no distribution. It's a lump model. What we're really looking at here is sub-watersheds or sub-elements across the landscape. In SWOT, that would be a sub-watershed. And in Kinross, we're really talking about hill slope plains that drain into the channel. And we'll look at that as we go through this presentation. All right. We characterize the watershed using different spatial layers, topography, land use, land cover, soils. We need other information as well, like the pour points that you already saw in the first tutorial. And so this allows us to describe what's happening across the watershed, and what those lines on there, those red lines indicate are the different modeling elements, sub-watersheds in this case. Okay, and you can see that it would have different terrain values and different land cover values and different soil values. Okay, for each one of these modeling elements, this is the distributed model. Okay, now one thing we try to do when we develop AGWA and essentially selected the models that we were going to use, we want to be able to run these models with readily available data. These are all national data sets that you can download and put into your computer. Or in the case of you're looking at a watershed outside the United States, we allow you to use FAO soils, or you can use different DEMs at different resolutions. But the point is that you have to have this spatial information to describe your watershed. And then we subdivide that watershed into these modeling elements. Each one of these modeling elements will have a different set of input parameters. Okay, so you can have one sub-watershed that is all agriculture, another one is an urban area, another one is a forest area. And again, we're going to model that integrative response. So we're dealing with high spatial variability. We're going to see a complex watershed response. And this is something that we can also change. We can actually go in and change, okay, the land use, land cover. And we can look at that response as well. So again, we can not only essentially use the original input data, the current conditions, but we can also change the conditions, especially related to the land use, land cover. We're using a lot of GIS functions, okay, in AGWA. You can delineate a watershed outside of AGWA using ArcMap. Okay, it's in the Spatial Analyst Toolkit under the Hydrology tools. Okay, it allows you to clean up your DEM using the sync tool, the tool that identifies essentially small sinks, depressions in the landscape. You can then fill using the fill tool, those depressions. Then you can use the flow direction tool to see and map out how water's moving through the watershed or through the area, as well as the flow accumulation tool that I'm going to show you next that shows you the accumulated flow through space. Okay, so in this example, I'm looking at the flow essentially direction tool, and it's what we call a focal function, a neighborhood function. And for every cell, it asks the question, which direction would I flow if I was water? And it's using the maximum drop. So it's using elevation values, okay, to determine the flow by determining the maximum drop to a given cell. All right, and that would be the direction that you would actually flow. And it's using a numerical scheme where 1 is east, 2 is southeast, 4 is south, and so on. Okay. So we actually know how water is flowing, okay, through the landscape. Now we can then, essentially this is interesting, what we're looking at here is flow direction, and where this is the Walnut Gulch experimental watershed that we're looking at, and you can see the red, it's flowing south, and the blue is flowing north, and the main channel is right in between there. So you can see you're getting the different aspects, okay, the direction of flow. Now, the flow accumulation takes the flow direction, and then it starts computing how many cells flow into another cell. So, for example, okay, in the flow accumulation surface, up here in the upper corner, we had 3 cells that flowed into that cell located essentially in column 2 and row 2, right? Starting in essentially the northwest corner, all right? So we had that flow accumulation. We accumulated water conceptually to that cell, okay? And then we can keep on tracking until down at the end, we have essentially 18 cells flowing into that cell. Okay, and so we can actually use the flow accumulation to identify the watershed boundary. Things that are zero is essentially the boundary of your watershed. We use flow direction and flow accumulation to delineate the watershed to a given pour point. Let's say this essentially occurs in that cell with 18. So we would get our watershed boundary. We also can determine where the channels are given the DEM. They're going to be locations with high flow accumulations. And each one of these cells represents a raster cell. So for example, if you're dealing with a 10 by 10 meter DEM, where each cell is a 10 by 10 meter square, okay, then basically this would be 10 meters, 10 square meters, not 10 square meters, 100 square meters, a 10 by 10 cell, all right, okay, and that's what we'll be looking at here. So again, we're using the flow direction and the flow accumulation to delineate the watershed, as well as determining the drainage, essentially the channel system within the watershed. This figure is just illustrating that, all right? You go from the DEM, you may clean up the DEM using tools like sync and fill, and then you use the flow direction tool to plot out the direction of flow, okay? And then you use the flow accumulation tool, and that helps you identify the watershed boundary, but it also identifies the areas of high accumulation. They're going to be the channel system. Now, in AGWA, we define the channel system using this process. We do not look at other data to define the channel system, like essentially flow lines, essentially provided by the USGS, okay? In order to be able to characterize essentially this watershed, okay, to essentially for AGWA, we need to use how the DEM defines a channel, not how other essentially information defines a channel network. So it's just strictly defined based on the DEM. So in this figure, I'm just illustrating what it conceptually looks like when we're done with this process. We'll take a watershed with topography. This is a watershed, I forget, watershed 11, okay, in Walnut Gulch Experimental Watershed. We do have a catchment pond here, which we're not including in terms of delineating the watershed. We then break that essentially watershed into, okay, essentially different response units. Okay, these are essentially modeling elements where we're going to model essentially the flow of water and sediment off of a hill slope, as well as we delineate the channel network. And then conceptually in Kinross, we take this information and essentially redefine the watershed in a series of rectangular planes, as well as linear channels. These channels are the same length as the channels that we actually see, okay, based on the flow accumulation tool. All right, okay. And so basically we also have a numbering system involved where we know what channels are flowing into the head of the watershed, what channels essentially are what modeling elements flow into the head of the channel, what modeling elements flow into essentially the channel from the sides, okay? Essentially, when do we basically have two channel systems essentially merge, and so on, until we actually represent essentially the watershed at the outlet. All right, so this is conceptually what we're parameterizing. We're going to come up with hill slope parameters for these rectangles, and we're going to have channel parameters for these blue lines, the channel systems. Okay, and we have a numbering system, so we actually know who flows into who. Okay, this is what we're going to be reading into the input file for Kinross in this situation. There are 4 ways to characterize a watershed. Okay, 2 of them are based on the threshold concept. The other one is existing stream networks. And the third one is identifying places where a channel will start. All right. So the threshold methods include contributing source area as well as flow length. Contributing source area is defining how much area, usually as a fraction of a watershed, okay, 2% of the watershed, 5% of the watershed, okay, essentially would be the point where you would actually have a channel start. All right, so we delineate the upper channels and then we start defining the lateral channels as we move through the system. Flow length really looks at the maximum length of the hill slope. So we'll go to the very outline of our watershed and then determine, okay, what is the maximum slope essentially we will allow before we have channels start. Okay, and then we start delineating, again, the lateral channels based on that. Okay, channel length is something we would use if we're looking at erosion modeling, where when we're dealing more with an erosion and runoff, we may use the contributing source area method. We can use existing stream network. That would be where we would take streamlines from the National Hydrologic Data Set and locate the end of the channels. We then use those end of channels as a channel initiation point. Okay, so the zero order basin would be above it, and that would be the start of the channel system. And then we just define the laterals and so on. Okay, and then we also can essentially, channels can still be defined based on the DEM. We just use essentially the known stream lines to identify the end of the channels, and then we use our regular process for the rest of it. Okay, and then we can also just have a point where we want a channel to start. One place we've used that when we have ponds, stock ponds on a watershed, and maybe our DEM would not, or the way we actually are essentially applying either contributing source area or essentially slope length, we may not catch that pond. We'd actually force, okay, the channel to start at that pond. All right, so we'd actually say you have to essentially the end point for the channel is at the outlet at the pond. So that's one place we've actually used channel initiation points. So again, in the last tutorial, you used the threshold approach, okay? And you can have different percentages, and that will lead to different representations, characterizations of the watershed, okay? As well as different flow lengths, maximum flow lengths. You get a different, essentially, characterization of the watershed. In this slide, I'm looking at how CSA would influence a watershed complexity. Basically, the smaller the CSA, contributing source area, 25% or 0.26 square kilometers, you would get, okay, a lot of modeling elements. And essentially with 2.5, you would get 44 watershed elements, and essentially with 29 channel elements, compared to using a CSA of 20%. In other words, that means every subunit, okay, response area, okay, sub-watershed would be 55 square kilometers in size compared to 6.9 square kilometers in size. And you only have 8, okay, watershed elements and 5 channel elements, okay. Okay, this would have a really big impact on how a watershed would respond, okay? Okay, in the 2.5, it's really dominated by the channel. It's very well drained, and the channels have a really big influence on your response compared to the 20% where you have these really big sub-watersheds with no channels. And so it's really being controlled by hill slope processes like essentially overland flow. Infiltration and overland flow will essentially define essentially how the watershed would respond. Okay. And note there's no initiation point until essentially that part of the watershed. So here's essentially 2 examples. Here's a watershed. This is actually in California. It's 162 square miles in size. Okay, I use a CSA of 1%. okay, the stream length, okay, was 103 miles. The average element size, modeling element, sub-watershed size, okay, was 1.3 square miles, compared to when I actually used a CSA, a 2.5, 2.5%, okay, my stream length was 71 miles. My average element size was 3.79 square miles. Okay, so it really does have a pretty significant impact on how you actually describe a watershed. You can see you have many more, okay, small subunits here, okay, compared to, okay, in this situation where your modeling elements are much, much larger, okay, but you have less channel. So what does this mean? Well, it depends on where you are in part, okay, but the smaller the modeling element, the greater the channel length, okay, that's just a given, okay. If you have ephemeral channels like we have here in southwestern Arizona, okay, you can actually see a decrease in runoff, high transmission losses, okay, because we have these ephemeral channels. And so we actually see water, or essentially runoff, decrease as we move downstream. Okay, and that essentially that increases that we have more channels. So we'll actually see a greater loss. Okay, perennial channels, you'll see an increase in runoff. Okay, the reason why is that when we have perennial channels, we can add a base flow component to it. I'll talk a little bit more about that in a second, but we can add a base flow component to it. So we see essentially runoff increase as we travel downstream. It's more efficient routing. You have more channels, so you can expect higher peak flows if you have a small CSA. Okay, you also should see higher sediment yield because you'll have more channel erosion. You also will have more spatial variability, weighted average a smaller area. Okay, the effect of rare types will be retained. Okay, so this is something to remember. Okay, the smaller your modeling element, essentially the longer the processing time. All right, so this is definitely one of the drawbacks. Okay, it will take longer to essentially do a simulation because you'll have more elements to actually have to deal with. Now, we've delineated these elements, okay, but we haven't parameterized them yet. So in both SWAT and Kinross, we have one set of parameters for each one of our modeling elements. Okay, either the subwatersheds in SWAT or the hill slope elements in Kinross. These are considered to be homogeneous planes. Okay, and we're going to come up with an input data set. Okay, different parameters where we've intersected topography, essentially land use, land cover information, as well as soil data. Okay, we'll see an information loss because we're going to come up with a single value for each one of these modeling elements. So there are definitely scaling issues here. Okay, the smaller the modeling element, the less information you lose. All right. Okay. And in AGWA, we're going to assign our input values based on a weighted average scheme. In other words, we can have different soil types in here. We can have different land use, land cover types. We can have essentially an area that's steeper than another area, but we're going to come up with an average value, okay, for this essentially modeling element. In this slide, I'm looking at several different ways you can actually come up with a single input parameter for a watershed. And depending on what method you use, you come up with different results. Okay, so in this case, I'm looking at curve numbers. This is used by the Soil Conservation Service curve number method. Okay, and this essentially small modeling element has two different land cover types. One land cover type, like essentially a rangeland site with grass has a curve number of 60, and another essentially 25% of the watershed, okay, has a curve number of 95. That's more like an urban area. So we have an area with 60, okay, which is a grassland, an area with 95, which is an urban area. The higher the number, the more responsive the watershed, the more runoff that you would expect. So 95 represents concrete, okay? 60 represents a site that is vegetation-wise fairly healthy and a soil with at least fair infiltration. Now, I can take these two values, okay, and I can basically come up with a single value to represent this area, either using a arithmetic average, a weighted average, the maturity, or the maximum value. Oops, sorry. Okay. And so with the weighted average, you would get a curve number of 77.5, and using the curve number equation, you would get a runoff value for 1 inch of rainfall of 0.053 inches of runoff. Now, when you use the weighted average, I acknowledge that the CN of 60 represents 75% of the area, and the CN of 95 represents 25% of the area. And you'll see that the curve number goes down, okay? The smaller the curve number, the less potential runoff. And so with the weighted average, I have a runoff value at 0.002 inches compared to the 0.5 when I use the arithmetic average. Now I can use the maturity, that's using the 60 to represent that area. I have a runoff of 0. In other words, I'm not even acknowledging I have this urban area, okay, with the high curve number. All right, they had essentially, it's a small area, but I would still expect a fair amount of runoff coming from that area. All right, now I could use an approach where I use the maximum value that I actually find, okay, within that subunit. Okay, if I use 95, I would get a runoff of 0.56. All right, much different than the other three, which are much smaller. Okay, I'm basically saying the entire watershed is responding, okay, like an urban area. Now, one of the problems that we actually see with the approach we use is that sometimes when you have an urban area, you have a lot of concrete. And if we actually essentially average that in, weighted average that in with essentially the surrounding area that is not urbanized, we'll have an area that can actually erode, okay, across the entire area, even though some of that area is concrete, okay? All right, and so it does lead to, you know, information loss as well as sometimes misrepresentation. And the smaller the size of your modeling elements, the less likely that will occur. That's one of the advantages of using small modeling elements. Model parameterization. We don't talk a lot about this in our tutorials, but you can, okay, you can parameterize each individual channel element, all right? Okay, you can come up with different, essentially, with the depth relationships, okay, hydrologic conductivity. This is very important if you have transmission losses. We recommend 0 for perennial channels. Okay, you can also set a constant base flow. That's down at the bottom for perennial channels. So you can actually have a constant input into the channel. Roughness, Manning's N. Armoring, erodibility of the channel system. It can be very high or very low to 0. Okay, you can have compound channels. Okay, we can have essentially like a natural riparian. Okay, we can also, okay, each channel reach can have unique set of parameters. Now, this is something that we do internally, okay, when we're actually looking at with the depth relationships, excuse me. We actually acknowledge, okay, the watershed size to that point, and we'll actually change for a given channel reach, okay, its geometry. But we do not automatically change, okay, the others like Manning's N. You'll set it for the entire channel system. You can go in and change it if you want, okay? But the software does not do that. It doesn't provide you with that automatically, okay? But this is something that you can actually physically do. I might add, you can also go in and remove channels, okay? Now that's something that maybe happens when you have urbanization. They'll go in and actually remove the natural channels. And that's something you can actually physically do as well when you're actually characterizing a site, is remove channels. Okay. USDA Walnut Gulch Experimental Watershed is located in southeastern Arizona. Here's the outline of the watershed over here on the right. Where I have my pointer is where the city of Tombstone is located. So if you've ever been to Tombstone, Arizona, okay, you've been in the Walnut Gulch Experimental Watershed. Now, one of the things the Walnut Gulch Experimental Watershed have done, okay, if they essentially developed one of the most intensive rain gauge networks. They've employed one of the most intensive rain gauge networks in the world. Okay, and one of the reasons why they did that is because most of our runoff occurs because of thunderstorms, convective rainstorms. These are storms that essentially have very high intensities in very small areas. So they needed to capture that variability in space. Okay, all right. And so they actually put out this really intensive, okay, rain gauge network. Okay, they also have essentially 29 gauge watersheds, 8 with essentially measuring sediment. Okay, the watershed was established in 1954, so we have over 60 years worth of record. Now, a lot of studies have been done on the importance of rainfall on hydrologic response based on, okay, this essentially wonderful rain gauge network that they've actually had. And I like to show you this picture down here. This is the outlet down here. This is Flume 1, okay, the outlet of the watershed. It very seldom actually flows here because we're dealing with ephemeral channels. But when it does see water flowing, that water is usually filled with sediment. So we do have very high sediment loads coming from this watershed. Now, one of the things that they've been able to find at essentially Walnut Gulch is that when you're doing modeling, okay, you usually see very poor predictions for small runoff events. Okay, in other words, you basically have essentially a large, essentially rainfall, you have very little runoff. That's due to infiltration, the fact that we're only seeing rain on a relatively small area. We have essentially these high transmission losses. Okay, so you can basically essentially get a decent rainstorm, but you still see very small, essentially volumes of runoff. Okay, and it's really hard to model those kind of events. Okay, and we're actually looking over here on the right, the water balance at Walnut Gulch. Okay, we average about 350 millimeters per year. Almost all of that is infiltrated into the soil, okay, and is evaporated back up to the atmosphere. Only 23 millimeters runs off of the hill slopes into the channel. A lot of that is lost, okay, through infiltration into the bottom of the channel. Over here on the right-hand side, okay, you're seeing a wave of water going down the channel. Okay, that white area is water, okay, and then you can see the dry channel bed. And so we see a lot of transmission losses in this system. And so we only see 2 millimeters of runoff per year. So we have 350 millimeters of precipitation, and it results in 2 millimeters of runoff per year on average. Okay, so again, we have essentially a watershed that we see rainfall, but we don't see very high runoff response, except for very, very intensive rainstorms. Okay, now we are measuring essentially rain gauge, measuring rain. We have a rain gauge network across essentially the watershed. Essentially, rain gauge measurements has been air about 3 millimeters. You add some wind, it can be as high as 5 to 25% error. Okay, and so we can also see okay, a high degree of error related to our measurements. And small areas uncertainty in rainfall can result in high uncertainties in runoff. This is something we know about modeling these systems. Okay. If you don't have a good estimate, this is true for all modeling, hydrologic modeling, I should say. If you don't have a good estimate of rainfall, you're not going to be able to predict the runoff response essentially accurately. Okay. And how well you represent rainfall has a big impact on how well you can actually model runoff response. Right. So in arid and semi-arid regions where we see this essentially these small runoff rainfall ratios, you are between a rock and a hard place. You can't expect any watershed model to make good predictions for small runoff events, especially without good rainfall observations. So again, this is something that we know we can usually model the big events relatively well, okay, but the small events, we do have a high degree of error. Maybe it's not really important because they're small events. Really, most of the runoff we see really is from that small set in terms of the total amount of runoff coming from a watershed. It's really a function of those few small, with those few large events. Okay, but again, we have to acknowledge that a lot of our events, the small events, we will not do a good job. This is a experimental watershed across the valley from Walnut Gulch. This is in Sierra Vista. Okay, we actually have two sub-watersheds they monitored here. One was a grassland, the other one was an urban area. These green dots are gauging stations. All right, we also measured essentially with the yellow essentially dots, okay, essentially the rainfall across this area. Okay, the blue is essentially the runoff from the grassland area. Okay, the red is the runoff from the urban area. Okay, the black is the precipitation. And we saw an increase in runoff from this urban area of a factor of 27. All right, okay. So we're seeing essentially the urban watershed is much more responsive compared to the grassland watershed. And so using this information, they had stream gauges, they had stream flow measurements. Okay. We're able to try to model the urban watershed, okay, as well as the grassland watershed. And we found, okay, that we usually had high model prediction uncertainty when we had a low runoff, essentially rainfall ratio. Right? Now, in urban watershed, we had a higher, essentially, runoff rainfall ratio. We were able to essentially model these events relatively well. Okay, and so the X's, okay, are measured runoff. Okay, the black line, okay, is our runoff response, and then essentially the other black line represents our uncertainty related to our response. Okay, so we have actually two lines. One is the hydrograph, the other one is basically the level of uncertainty. And you can see that in the urban watershed, we have a lot less uncertainty, a lot less gray area. These are essentially these are much larger events, essentially with a lot more, essentially a volume of runoff, has much higher peak flows as well. Okay, for two of these, we did exceedingly well. Okay, the top one and the bottom one, and the middle one, we did better than any of the grassland watersheds where we had a high degree of uncertainty. So these bands indicate, okay, uncertainty related to our modeling results. And what we actually found, okay, that we actually did fairly well, again, when we had this basically high, essentially, runoff rainfall ratio compared to a low essentially runoff rainfall ratio. Okay, so this is a given. Okay, if you have basically a lot of small events in your data set, okay, it's going to be harder to calibrate. It's going to be harder to essentially come up with accurate model results compared to the larger, essentially, events. This is important, especially how you use this model. Like we use this model for a lot looking at post-fire effects. So we actually don't look at the events, the small events. We're only looking at the relatively large events because that's where we're going to see the biggest impact in terms of potential flooding as well as on erosion. So we really only concentrate on events that have a high, essentially runoff rainfall ratio. Now in AGWA, okay, there's different ways you can characterize rainfall. You can use observed data. Okay, we've already talked a little bit about this, but the more rain gauges, the better. Okay, we can apply a Thiessen approach to essentially distribute the rainfall across the watershed. Okay, or you can, I've done this in some of my research work, take essentially the rainfall measurements from the gauges, and I come up with an interpolation, okay, of essentially rainfall pattern. Okay, you can use design storms. Okay, this is something we do with Kinross a lot. Okay, we want to see how the watershed is responding after fire. Okay, so we'll actually select a 10-year return period event and a design storm, essentially hydrograph. And we basically, okay, essentially will essentially model the before and after essentially a fire based on that design storm. It's a relatively big event. You can use a stochastic weather generator. ClideGen is the one we typically use. Okay, I will add that essentially here in Tucson, the ARS is working on essentially developing a data set so you can use ClideGen, this essentially stochastic weather generator worldwide. They've already done with essentially Africa. They're working on South America now. This is also something we use in conjunction with essentially the rangeland hydrology erosion model version of Kinross. Okay. We also have a tool where you can use radar data. This is only for Kinross 2, only right now in the United States. All right. And what you would do is use AGWA to characterize your watershed. Okay. And then you link it to another tool that takes the radar data and then distributes rainfall across your watershed, and you model the response. Okay, this is not something that is in AGWA. You would have to contact us about this. And this is some way you have to, in many cases, you have to contact us about essentially the weather generator as well, especially when you're actually want to use it for Kinross. Okay, so again, there are different ways you can get this rainfall data, either using observed data from essentially weather stations, okay, or using design storms, a stochastic weather generator, or radar data if you want really high resolution data. Now, one of the things that we have actually done, all right, okay, is that we have used these design storms, 24-hour rainfall distribution, essentially patterns that were developed by NRCS, or essentially, and there's actually 3 of them in their original set. They have actually modified this, where there's actually essentially other distributions for other parts of the country. In this case, we're only looking at 3. 1A, as well as essentially 2, which is most of the country, and then 3 down here along the coastal areas. This is usually related to hurricanes. All right, we use essentially type 2, here in Arizona through a lot of the Mountain West. This is where you expect your significant essentially rainfall event to essentially have a shape that you would get from an intensive short duration rainfall, i.e. a thunderstorm. A lot of our essentially flooding events, especially on small watersheds, come from thunderstorms, and so this type 2, right in here is for a thunderstorm, where it's relatively flat, a period of very high, intensity rainfall, and then it's relatively flat again. So it looks something like this, all right? If you're basically in the Pacific Northwest, it's basically a little flatter. They have more frontal systems there. So they basically essentially have a very peaky hyetograph. They have a relatively flat hydrographic, in other words, uniform rainfall over time. Right? So again, you have different essentially shapes of rainfall, the hydrograph essentially given what part of the country you're in. All right, this is my last slide, then we'll open it up for questions. Model verification. How well can you actually do? How accurate are your results? And how accurate do you need your results to be? It's really a function of how you're using the model. So for example, if you're using a model for experimentation, okay, you really don't need high degree of accuracy. What you need is that model works correctly. It's valid for your system that you're trying to model. So it's working correctly. If you increase in temperature, you see an increase in evapotranspiration. All right. So we use these models to study biophysical systems. All right. And we just have to make sure that they work correctly so we know essentially cause and effect, essentially within these biophysical systems. But if you're using the model for regulation down in the bottom here, well, you probably want a high degree of accuracy. Okay. But in order to do that, you need data. You need streamflow data. You need precipitation to calibrate and verify your model. Okay. So you can validate it. You need essentially you can calibrate it, and then you can actually test it to see how well it's doing on an independent data set. All right. Okay. But you need data to do that. And that's a really big issue because in a lot of cases, we're going into areas where we don't have streamflow data. We don't have good, okay, precipitation data other than maybe radar, okay, which is more extensive. Okay. So essentially, this is an issue to get that calibration, to get your model fine-tuned, so to speak. All right. So there's very few places with enough data to truly, for verification, for really testing your model to see how well you're actually doing. Now, this middle case is where we essentially apply models a lot. Okay. And we apply it from a planning point of view, from a decision-making point of view. Okay. We need to understand basic trends and how streamflow response, erosional response will change under management or under disturbance. Okay. All right. Essentially, we need a model that we know works correctly. It's valid for our area. Okay. It's been tested in different locations, but it hasn't been tested at this specific location, okay, because we may not have the data to essentially do that. We don't have streamflow data, precipitation data. So moderate accuracy is acceptable. Really, to make decisions, there's been a lot of research on this, okay, and the decision-making literature, you know, getting the magnitude differences correct is more important than essentially for making decisions. All right. In other words, I have two treatments on the watershed. One caused runoff to decrease by 5%. The other one caused runoff to decrease by 25%. Which one would actually you use? All right. Okay. Or it caused essentially erosion was decreased 5%. Erosion would be caused by 25%. Which one would you use? As long as those differences are correct, regardless of the absolute values, you're more likely to choose B over A, the one that gave you 25% decrease. Okay, so we call this a relative change analysis. We've talked about this already. Dave did earlier. Okay, so where we actually have before a treatment, before a disturbance, okay, and then after a treatment, after a disturbance. A treatment may be erosion control method, or essentially we'd be looking essentially before and after a wildfire. Okay, we're doing a relative change analysis. We're seeing not only how a watershed is changing, but across the watershed, how is essentially runoff and erosional responses changing. This is really good for making decisions. Where do I want to go in and put in erosion control practices? Okay, after a fire, where do I want to put the hay? Okay, those are questions you ask. I want to do it over in that watershed because the differences are greater. All right, okay, based on our modeling results. I will add relative change analysis, or essentially applying a model, even though it's not been tested in an area, can give you information you can use for design, especially if you're dealing with small structures. Okay, so people use the curve number a lot with this. Okay, they've never tested the curve number on the watersheds they're applying it on. Okay, they take it for essentially, they just assume that it will work well. Okay, and they'll come up with essentially the metrics they need to size a culvert, size a small bridge, okay, size a stock pond, et cetera, so forth. So this essentially type of modeling can provide you, usually using design storms, information you can use to come up, essentially give you the design criteria that you need. How big does the culvert need to be? How big does the spillway need to be, okay, on a small stock pond, all right? Okay, so this is something to think about, especially when you're dealing with precipitation, because as I said before, okay, I'm sorry, with this result, okay, for small events, you're not probably going to do a good job anyway. And if you don't get good rainfall data, you still can't model a system essentially well, all right? And so in many cases, we don't have the actual event, okay? We don't know what the actual event will be, okay, like post-fire. So using design storms and stuff is a way to get around that. We look at relatively large events. How would that system essentially respond? Do we have to worry about downstream flooding? Where do we need to worry about significant erosion? These are things that you can actually get, even though you haven't gone in and calibrated a model for a specific location. Right? All right. All right. So I'm going to essentially stop sharing. I always get through this a little fast. All right. Any questions?